Hello. We'll be going over how to run a GOMC simulation using the Gibbs Ensemble via MoSDeF. My name is Brad Crawford. I would like to thank Wayne State University for support of this research, as well as NSF, specifically for these grants, which are for GOMC and MoSDeF. For this example, we're going to go over a Gibbs Ensemble using MoSDeF to generate the files. Specifically, we're going to go over a Gibbs NVT ensemble. You can either use NVT or NPT ensembles. I'm choosing the NVT ensemble here because typically it's a more stable ensemble. The first thing we need to do is import the packages for the force fields, and you'll notice I'll use FF for force field throughout this example. And just as a reminder, the residue names are treated as molecules. So if you have a different molecule, it's going to need to have a different residue name. That's just how GOMC does it. And unlike the previous examples, these residues can have different force fields. I alluded to this before, but we'll actually do it in this example. So you do this by selecting a residue here as a key, and then whatever force field you're going to use for that residue. And I stress caution with doing this to make sure the force fields are compatible, because if the force fields are not compatible, then there is an issue with the calculations and they very well could not be right. So you always want to make sure your force fields are compatible. We're going to import the files that we need. And then in this line, we're just going to select from the files, the water force field files. In this case, we're going to use the SPCE force field, which is located in the files. We're going to load water through a smile string. We're going to change the residue name to H2O. And then we're also going to minimize the energy of the water using its force field. And then we will do the same for the ethanol. So this is going to be a water ethanol mix. And we're going to use the OPLSAA force field for ethanol. We're going to also build it through smile strings and then name the residue ETO and then minimize ethanol with its force field. And then we're going to use a force field dictionary to specify the water molecule or residue go to the water force field, and the ethanol residue or molecule go to the ethanol force field. So basically, we're saying water is going to use the SPCE force field, and ethanol is going to use the OPLSAA force field. And then we make a residue list with ethanol and water. And then we also want to fix the bonds and angles of water. So we'll run that. Should take a second. It's done. So now we will build the main simulation box. So we're going to build a water and ethanol liquid box and a water and ethanol vapor box. In this simulation, the GEMC simulation, we're going to assume that we're doing a vapor liquid equilibrium because the Gibbs Ensemble simulations are very good for that. So in building the liquid box, we just specify water and ethanol as our compounds. And then in this case, we can actually specify the density. So we want 950, and this is in units of kilograms per meters cubed. From this selection, we also need to specify the compound ratio. So we're going to do an 80:20 ratio of water to ethanol. And then the same thing with the vapor box. And we'll specify the box dimensions for the liquid at 3 nanometers in each direction, X, Y, and Z, and then 8 nanometers for the vapor box. And in the vapor box, we're going to keep the density at 100. That's kilograms per meter cubed. So we'll run this. Might take a second to build the box. It's done. Now we're going to build a charm object as we did in previous videos. We're going to add box 0 here. Box 0's name for the PSF and PDB files. Box 1, and then its name for its PDB and PSF files, whatever we want the .imp file named, or the force field file. And then here's where we'd add that force field dictionary in the force field selection, which will allow us to use 2 separate force fields, one for water and one for ethanol. And then we add the residues list, which is the total residues listed in the system. We're not using a bead to atom dictionary because this is all atom systems. We're not fixing the residues in any box, but we are using the GOMC fixed bond angles, which, if you remember, this was just for water. So we're going to fix the bond angles of water. And then there's also an option here to reorder the PSF and PDB files. So no matter how they were built in the system, you can put them in a certain order. And in this case, we're just going to change the order to how we have them listed, and that changes the order to how they're built in the PSF and PDB file. It just basically reorders them based off the residue list. So if you hit true here, it'll reorder them the same way that is in the residue list. Now we're going to write the force field or IMP file, the PSF and PDB file, and the GOMC control files. So we get the force field or IMP file, the PSF and the PDB file here. That's the write command, and then the write the GOMC control file. We just enter the charm object, whatever we want to name the control file, and then GEMC underscore NVT for the NVT ensemble version of the Gibbs Ensemble, and then 100 steps, temperature of 300. So it's important to note, since we're using OPLSAA, we need to use geometric sigma true, because OPLSAA force field does have a geometric sigma. And then I picked some variables to change to show some different options. So I'm going to select the R cut to 12. You know, it's best to do whatever the system was designed for, or if you validate it to a different R cut, that's fine too. And then one other option we have here is we can do R cut Coulomb box 1 at a higher value than R cut. So what that's going to do in the vapor box, since there's not a lot of molecules, actually extending the short range calculation can actually speed up the calculations because there's not a lot of molecules. You would not want to do this in a liquid box because it would increase the cost of the calculations. It's maybe something to learn with time and experience, but just for an example. And then I want to change the Monte Carlo move ratios from what is standard. So I just picked displacement frequency, rotation frequency, intra-swap frequency, swap frequency, regrowth, crankshaft move, volume frequency, which isn't applicable, so it's 0, and then the multi-particle frequency. So the multi-particle frequency is it moves all the particles in the box at one time. This is an expensive move, so you probably don't need to do it a whole lot. So we selected around 1% to do it. So we will run that, and it'll write those files for us. You see some of the outputs. And you can see here the force field selection, the water goes to the SBCE force field, and then the ethanol goes to OPLSAA force field. And it's important to note too that we're pulling the standard force field from MoSDeF, and we're using our own SPCE XML, and you can build your own or import other ones. You can use a combination of the standard force field and then ones you imported or built yourself, which makes it very flexible for the user. We're going to go through this example 4. and the terminal window for the Gibbs Ensemble. First, we just want to note that these files here, both the Jupyter Notebook and the Python file are the same files. They're just one's formatted in Python and one's formatted in Jupyter Notebook. So we just want to find the location of this file and keep a note. I'm already in my active environment that supports MoSDeF. That is mbuild and Foyer. So we just want to CD to this directory where these files are, Python file specifically for water and ethanol. And then we'll just delete the file name, which is drag it in and drop it to the terminal window and hit enter. And that brings us right into this directory. Then we simply type Python, and we can also GE and then hit tab, and it'll finish it except for the PY because it has a matching Jupyter Notebook extension. So if we type that in and hit enter, that'll run the script and generate the force field, PDB, and PSF files, as well as the GOMC control file we went through in the Jupyter Notebook. Just see there's a few warnings, but we're okay because they don't really affect us, and that would be expected. What we're seeing. See, these files are built, the PSF file, the IMP file. All the files are built. So next, we want to execute the GOMC simulation since we have all the files to do so. And as I said before, you can type the path to the binary GOMC file, or you can get in its bin directory after you create and build the bin directory via the GOMC instructions. And in this case, we want to run the GEMC version of GOMC since we're running the Gibbs Ensemble. So we can just drag this in, drop it, and we'll plus P2 since we want to run 2 processors. And then we know the name of this file that we want to run, the GOMC control file. We can just type in and hit tab, and then it finishes it for us. So, and then we want to output it to the log file with the name out.dat. And that's all we need to do. Hit enter, and we're running the GOMC simulation. It'll take a second. You can see all these new files were generated, the bulk output file, and then our log file out.dat. And then it's done. You can open the bulk data file or just make sure it outputs something. We can see it is outputting 100 steps as we thought. Thank you for watching. Have a good day. Here are the references used for this example and previous examples. Note the numbering is kept consistent through the examples as much as possible.